dryer which wants to blow out stuff, and then there is that little sucker that wants to suck something in, and it succeeds to some degree. It's not as powerful as the +3 though. Have we lost all information about field strength? We had earlier with these arrows, we had the length of the arrow, the magnitude of the field was represented. Yeah, you have lost that, but there is still some information on field strength. If the lines are closer together, if the density of the lines is high, the electric field is stronger than when the density becomes low. So if you look, for instance, here, look how many lines there are per few millimeters. And when you go further out, these lines spread out. That tells you the E field is going down. The strength of the E field is going down. It's the 1/r² field, of course. If you want to make these drawings, what you could do to make them look good, you can make 3 times more field lines going out from the plus in this case than return to the -1. So the field lines are very powerful, and we will often think in terms of electric fields and the line configurations, and you will have several homework problems that deal with electric fields and with the electric field lines. If an electric field line is straight, so I have electric fields, get some red chalk. Say we have fields that are like this, straight E field lines, and I release a charge there, for instance a positive charge, then the positive charge would experience a force exactly in the same direction as the field lines, because the tangential now is in the direction of the field line. It would become accelerated in this direction and would always stay on the field lines. If I release it with 0 speed, start to accelerate and it would stay on the field lines. In a similar way, if we think as the Earth as having a gravitational field, with 801 we may never have used that word gravitational field, but in physics we think of gravity also being a field. If I have here a piece of chalk, the field lines, the gravitational field lines, here in 26/100, nicely parallel and straight. And if I release this piece of chalk at 0 speed, it will begin to move in the direction of the field lines, and it will stay on the field lines. So now you can ask yourself the question, if I release a charge, will it always follow the field lines? And the answer is no. Only in this very special case. But suppose now that the field lines are curved. So here are field lines, as you have seen in those configurations. It's very common. If now I release a charge in here, say I have a point charge here, it will experience a force in this direction. So it will get an acceleration in this direction. So it will immediately abandon that field line. And so if now you ask me what is the trajectory of that charge, well, it could become very complicated. I really don't know. Maybe it's going like this. And by the time it reaches this point, what I do know that then the force will be tangential to this field line, so will be in this direction. And so as it marches out and picks up speed, locally it will experience forces representative of those field lines, and so the trajectory can be rather complicated. So field lines are not trajectories, and not even when you release a charge with 0 speed. Only in case that the field lines are straight lines. Let's now look at a field configuration which Maxwell himself, the great maestro, in some of his publications put there. It was a ratio 1:4. And whether it is +4, +1, or -4, -1 is not important, because that's just a matter of the direction of the arrows. But Maxwell didn't put arrows in. So I leave it up to you. If it's +4 and +1, you have to put arrows going outwards. And what you see now here is this air blower effect. Think of them as both being positive. So there is the +4 trying to blow air out like a hairdryer, and the +1 is trying to do its own thing, and so you get a field configuration, field lines, which are sort of, not perhaps easy, but you can sort of imagine why it has this peculiar shape. If you put a plus test charge in between the 1 and the 4, then the 4 will repel it, but the 1 will also repel it. And so there's going to be a point somewhere, probably close to 1, whereby the two forces exactly cancel out. Therefore, E will be 0 there. In a similar way, between the moon and the Earth, there is a point not too far away from the moon, where the gravitational attraction from the Earth and the gravitational attraction from the moon exactly cancel each other out. That's not too dissimilar from this situation. So when you have charges of the same polarity, you always find in between somewhere a point where the electric field is 0. Let's now go to a very special case whereby I make the two charges equal in magnitude but opposite in sign, and we have a name for that. We call that a dipole. The plus charge is here and the minus charge is there. Situation is extremely symmetric, as you would expect, because they have equal power. There's one air blower upstairs and one vacuum cleaner downstairs. If you're close to the plus charge, notice that all the field lines go away from the plus. And if you're close to the minus, notice that all the field lines come in on the minus. You expect that. If you are far away from this dipole, now you have a problem. Before we had a +3 and a -1. And when you're far away, the +3 wins. So it's like having a +2 charge. If you're far away, you always expect the electric field then to be pointing away from the equivalent charge of +2. But if you add up plus and minus and they have equal magnitude, let's say +1 and -1, you get 0. So neither one wins if you're far away. And notice carefully, if you're very far away, indeed you do not see arrows either pointing out nor pointing in. Nature cannot decide. There isn't one that is stronger than the other. And that makes dipole fields very, very special. In the case of the +3 and the -1, if you're very far away, it's like having a +2 charge, and the E field, when you go further and further out, will fall off as 1 over r squared. With a dipole, your intuition sort of tells you that it will probably fall off faster than 1 over r squared. And that is part of a homework assignment that you have this week. In fact, I can already give you the answer. You have to prove it. If you're far away from an electric dipole, the electric field falls off as 1 over r cubed. It goes faster than 1 over r squared.